Good afternoon, everyone. Thank you for the invitation. And as Camilla said, today I'm going to talk about Europe's leading outdoor living lab, which is Dall Living Lab. And I'm going to tell you a little background about how we work in the lab, and then I'm going to explain how we are working with data-driven applications and digital twin infrastructure in order to promote the use and fair use of data within a city environment. I've been working in tech R&D for the last 10 years and was actually employed here in Skylab for 3 years, so it's really great to be back. Dall Living Lab is located in Albertslund, and we are a physical testing and experimentation facility for IoT, for AI, for public infrastructure, and for everything to do with the activity between buildings, so things like traffic and environment and so on. We work where we have technology providers on one side, and we have municipalities and cities and decision makers on the other side, and we try to build a bridge between these two type of activities or actors in order to better explain the potential of making city AI and city data-driven projects. We're a part of a national organization called We Build Denmark, which is a cluster organization which facilitates public and private partnerships around the themes of public infrastructure. So we are interested in everything to do with modern city living and improving the conditions for city life for the citizens. We have a very broad range of partners, everyone from people that come with technology or data, people that can work with these technologies, platform providers, advisors, software companies, and so on. We have a standardized way to come into the lab where there's a fee for a business to come in, and the services that we provide to them are exposure, they are involvement in projects, and they are the potential to accelerate your business or to explore new business opportunities that you may not otherwise have access to. We also have a visitor service where we invite delegations from around the entire world to come and see the latest developments in Danish and European smart city developments. And here we see a lot of interest in what are the latest regulatory applications or laws that are being implemented or coming in the EU, and how should you as a business or service provider relate to these. And you can see these kind of activities here where we go out on tours and we have various kind of workshopping activities, all designed to upskill employees and to share knowledge about what's going on in the world of technology. And what we also do with our partners is that we involve them in projects. So we have, for example, some funding where we can run 2 to 3 smaller projects per year. And one of these I'm going to explain now is about the predictive maintenance of bicycle paths and roads, where the typical municipality today does not have the resources that they need to take care of all of these kind of damage on the road. And road damage is something that causes secondary effects such as increased pollution and noise, poor quality of life for the people that live in the area, also causes damages to vehicles. So the idea with this project is that we have a couple of private actors that do computer vision scanning of an area and produce a geolocated data set, which is what type of damage is this and how severe is it. And what we want to do in this project is to then take some historic data over a year and then ingress other types of data about traffic activity and so on, and use that to drive a predictive model so a municipality is able to see, for example, these cracks will become potholes in the next 6 months, so it makes sense to make an intervention today so that you don't have to make a more costly intervention in 6 months' time, for example. And the output of this will be, again, another geolocated data set where these exclamation points are the most relevant type of damage to address today. We've also been involved in a larger national projects, for example, Greenway for buses, which is about providing optimization mechanisms to allow public transport to go through intersections without being impeded, and therefore improving the quality of service for example, a bus operator. We also have a project now with the photonics department of DTU, which is about LED street lighting. So a secondary unpredicted effect of the LED revolution was that animal life was affected because of what we see as a peak in the blue part of the spectrum in an LED light. And this goes in and it disturbs the ability of an animal to produce melatonin, so they can't sleep, feed, or breed properly. And what happens is over some period of time, 10 years, we will see a massive reduction in the amount of animal life and biodiversity in a given area. So what this project does is that we have various technology providers and data providers that can come in. They can install devices onto our street lighting, which measures both the light that's coming out of the street lamp and the surrounding area. They have a database of how the spectral content affects different types of animals that are living in our area. And they send a message back from their cloud, which can adjust in real time the distribution of the lighting. And what this should mean is that we can establish the biodiversity again, which has been affected as a result of this. So that's very briefly about how we work with different partners and the kind of technology and the domains that we work in. And this results, of course, in that we have a lot of data that's being produced in the lab. And what we are doing now, a current project that we're working on for the next few years, is that we want to go from ingressing all of these data from IoT devices, fixed infrastructure, data that's being provided by, for example, mobility operators, which you can buy on a limited time period. And then we want to go all the way over to an application layer where we can build, for example, dashboards. We have a virtual lab, which is a gamified engine where you can explore the lab with VR glasses or on your computer. And we do that by adhering to various type of standards, laws, architecture, regulations that are coming out of EU, or maybe as things that are components that are available that have been designed on the background of these things. Two of the main standards that we're looking toward are what's called FIWARE. This is an ecosystem of technology components for building applications, for handling data and so on. And smart data models, which are semantic ways of describing different types of things that you may observe in a city environment. So smart data models, for example, now when you buy an IoT device, you will have some kind of proprietary description of the data that comes out. So you have a water measure or you have an environment measure. It's really up to the vendor themselves to choose how they describe their data and how they expose it. And when you work with these kind of data and you have hundreds of devices, it becomes a massive effort to align all of these data together. So smart data models are standardized ways to describe these kind of data. And there are a lot of different sectors that are represented within this modeling. And there is a very standard way of laying out these kind of data. So if it's a vehicle, an observation about weather, the environment, a person, everything has the same technical structure, which allows you to kind of hop over a lot of the data integration work that you may do. And then on the other side, with the FIWARE Open API, there are ways to write to devices, to read, update, get data, and so on and so forth. And this effort is a partnership with KMD, who are a large company that provides software to the public sector in Denmark primarily. And they are owned by a company called NEC Japan, which is one of the largest electronics companies in Japan. And they also have a lot of influence in the public technical infrastructure in Japan. And what NEC do is they are very deep in developing FIWARE components and developing smart data models. So we have a very short distance between the technological infrastructure and the kind of use cases that we wish to exemplify. So if we think about the holistic view here, what we see our digital twin is as a thin layer between a very complex and heterogeneous data landscape and then some applications which can be deployed to a given person or person's department about a given problem that they're sitting with at the moment. And one of the key things about this is that typically in a distributed IoT setup in a city, you are missing a lot of context about how you link your data together, what does the data mean, how do I understand the data as someone that works in a municipality. So KMD provide this data context platform, which is built on these technologies I mentioned before. And the idea here is that we transform the data into smart data models. We create links between the different types of data. And then we structure this in a way where we have a very standard way to get access to these data. So in the holistic way, yeah, we have a city area which contains hundreds of different types of devices and data sources. We have vendor-specific interfaces. So you buy a device has its own API, has its own CMS layer, and then you get that data depending on how the vendor decides. There is a great deal of complexity within this area, and that's something that's going to be the way it is for the next 10 years anyway. The next part of this is that we have an automation to get the data into a platform. And then we map these data to smart data models. So when we have, for example, an environmental sensor, what we want to map this to is a description of the air quality, the weather, the environment, and then a data model that describes the device. And the device will have parameters like power consumption, network strength, uptime, the time since the last calibration, and so on. And then we expose these data through an API where everything is always described in terms of an entity that has attributes where they have values. And the way that you can request these data is that you describe a time, a space, and a type of data that you want to get. So for example, you can go into the system and say that you wish to have some data from or to, before or after, also during an event. So you can say if you have a representation of a football match, you can say during this football match, how much traffic was there? And then you also have spatial ways to get the data. For example, get all of the data that's enclosed within this polygon, or that is a certain distance from a point. And then the resulting data object will look like it does there in the top right, where it has a standardized name, and then you have a setup here where you can see, for example, the attribute name, which could be PM2 or PM4, and then a value. And this is always the same. So if you have, for example, a vehicle measuring, the entity would be a vehicle, and the attribute could be speed, and then the value could be 25. The same if you have a pedestrian, you would say what's the number of pedestrians, they might have a direction, and then everything will be described in the same way. And this is kind of revolutionary from where we are today in the distributed data space, because it's very challenging to build applications where you have to put a lot of time into harmonizing your data. So for example, here we have a very, very rough design of an application, and all it does is produce these radar graphs. But this could be anything. The point is here is that by changing the request only, that's the data ingress part, I can reuse the same application to build different types of insights. And as long as I can describe what I want to know in terms of time, space, and type, I can reuse the same application layer to build different types of insights. And in terms of how do we actually get the information about time, space, and type, there are hundreds of standardized tools and things that we all can relate to that we already know about how to do this. Graphic elements such as maps and date sliders and graphic elements. Could also be that we can ingress an Excel file that describes your job function and some kind of update frequency. So people that are out doing the daily work, they get some daily update about the devices in the area. Maybe the manager gets it once a week, head of a department gets once a month, and then the city mayor gets once a year. And it's always the same application that's driving this. So we go from a place today where we have to do a fair amount of pre-processing, and before we even got the data, we have to source the data for first thing. And then we have to do a lot of pre-processing to make sure that we can compare, for example, the vehicle measurements from 2 different camera systems. And then we will usually have some kind of standardized, or let's say a single-use user interface which is specific to the application that we're looking for. And we have this generic application body. What we will be doing tomorrow is we will simply just ingress the data. it will be the same format for everything, the same mechanism to get the data in any space, in any time, and of any type. We can then reuse the central part of our application across these different data types and then use more time to build a nice UI or to integrate with the kind of tools that the municipalities currently use. Our observation from working with municipalities is that they will typically buy a hardware system that has a software vertical. So they have a CMS system for their traffic measuring where they can look on a map and they can see what the traffic activity is in their city area. And then they'll have another platform which is doing environmental monitoring, and then they have another platform which is doing flows of people. And it makes it very challenging to do comparisons across these domains. As a human, you have to look at some different interfaces. And on the machine level, you're going to end up with a lot of integration work. And you might be able to solve your integrations today, and then tomorrow, when there come new devices, new technology and so on, you have to reiterate this process. So one of the points of this is to really free up the domain for application developers. And today we have this analog doll area where everything is observable and turned on. And we have a digital twin area where the power is essentially turned off until we begin to deploy applications. So if we have, for example, an environment time series predicting mechanism or application, this could be used by a greenkeeper who wants to find out what kind of plants and trees do I need to plant in this green area in order to minimize pollution from the road that's next door, in order to dampen the noise for the people that are living and working in the area, and so on. So they're able to get these insights by deploying this specific application in this specific area, and this could be in real time or it could be historic. And then we might have the municipality want to look at speed infractions on a specific road in real time. And we may then have a private company that wishes to use the city data to benchmark the quality or the impact of a program or a service that they are trying to roll out. And all of these things are interchangeable. So anyone, any actor can use any of these type of applications in any place against any kind of data because everything is standardized. And where we're looking at going here is, of course, doing some AI away from the edge. Now we have a lot of edge solutions that are doing AI, computer vision, and so on. And we want to be able to do AI holistically on the whole data set. So in addition to these smart data models, which are standardized descriptions of data, there are also what are called semantic schemas. These are ways that data are described. So here you see, for example, the description of what does lantern height mean and what is a circuit. There are also explicit linking mechanisms between data models. So if we, for example, observe a failure in a lamp, we can see which control cabinet is supplying power to the lamp. And then in the control cabinet data model, it has an owner. And then we can look in the organization model, look up the owner, and find out what's the telephone number for the maintenance team. So we can very easily build a mechanic that calls the maintenance team, gives them the location, the type of error, as soon as the error happens. And today, I know because we do this every day, this is a very long process of fixing errors with a lot of different actors, a lot of information exchange, and there are a great many knowledge gaps in these kind of processes. So it's really we're trying to compress all this together and make it so that anyone can get these kind of insights. And there's also a convergence, a very interesting convergence now between new kind of consumer-grade AI tools, large language models, pre-trained transformers and so on, where we can provide the data and we can provide the semantic data model and ask a GPT to make a summary of what do these data mean given this context. And here we see things like application of the correct unit of measure, grouping of similar types of data, descriptions of how things evolve over time, and also contextual evaluation. For example, this amount of pollution in this area is potentially harmful to humans. And this information is not explicitly available from the semantic model or from the data itself. It's something that the language model can calculate itself based on its own training data. And where we'll be going in the future is, of course, using GPTs to produce all kinds of visualizations and graphs, also generating code to build graphs. And one thing that we need to know beyond the measurements and so on is what kind of area is this measurement being taken in? So up here, for example, if we have an environmental point right there in that intersection, that a CO2 level means something different than it would if it was here, because we have all of this green infrastructure here which is capable of absorbing the CO2. So one thing that could be really interesting to have is how much green coverage is there in this area, so we can kind of dampen or adjust some model based on that. And then maybe in 5 years' time or 6 years' time, we will be able to have a system which can ingress any type of request. So it could be from any kind of input. It could also be Excel file, speech to text, or whatever. And then we have a generic AI-driven application in the middle that's capable of producing any kind of output. And that means that we go from some desire to know something to a familiar type of output. And this is really, really important because we cannot expect people in municipalities and the end users of these systems to work with data directly. They will always be working with applications that encompass the data somehow. We advise strongly to work with standards if you're an IoT company or a data processor. And we will also say that the measurements alone are not enough. There must be some kind of semantic description of where the measurement is happening, what type of measurement is it, what does the measurement mean? And this is something that we hope to address in the development of our local digital twin. Thank you for your time.
Thank you so much, Ben. Super interesting to get that additional layer on our cities. Let's see if we do have a lot of people here today. Do we have any questions in the room? Yes? I'll bring your mic.
I was inspired by your, sorry, talking too loud. I was inspired by your realization that LED lights affect biodiversity.
Yeah.
And I was thinking, why not work with KU in the biodiversity department or biology department and use keystone species and indicator species as a type of Internet of Things so that you can also control environment, what's healthy, what's not. And also it's very much conducive to the area that you're in.
Yeah.
What is healthy for that area?
Yeah, yeah. On the biological side here, a primary challenge that we have is how do we validate that this has been a success? Because we are talking about a time scale that may be decades long. So the way that they understand how this works is that they've done lab experiments with exposing animals to different types of light, and they see, that this actually inhibits melatonin production. So we have a kind of informed assumption about how this technology will work. But it's a good idea, but we need to be able to measure today whatever. I'm not a biologist, so I don't really know what the parameters would be. And then maybe in 5 years, we're capable of doing the same measurement again, and then in another 5 years and so on. So it becomes a challenge to validate these kind of softer kind of efforts. If we have, for example, traffic optimization, it's very, very easy to validate that because we can just look before and after. We see an immediate result. This kind of biodiversity thing will be a much more longer-term project. And we have DTU, Electro, Photonic. They're now together, I believe. So they're the academic lead on this project, and it's them that's making these kind of decisions.
We have a question down here.
Yes. Christian Hvid from Department of Civil and Mechanical Engineering. This is a talk on city-scale digital twins, and I think that buildings are a major component in a city. So and there's lots of data coming from buildings. Lots is locked and is mainly unused in many situations. How are you working with building automation companies, building management systems, semantically deriving the data and the information from all these building service systems, and how do you think that is going? Is it going good, or is it a lot of trouble and a lot of silos where everybody wants to stay in their own silo?
Yeah. The very short answer is that we in Dol, we do not have any, we do not collect data from buildings at all. That has been a conscious choice, and it's also kind of based on history. We came from working with streetlight infrastructure, and then we went over to outdoor IoT, and then traffic systems, and so on. The issue with the data from buildings is that we don't own it. So in our area, we have a mandate from the municipality to install devices outdoors, and we own all of the data. As soon as we step into a building, we're in a completely different space, in a different regulatory space and a different legal space. And building owners are not the most, they're not at the front of the pack in terms of exposing their data. And I think also I saw you gave a presentation last month in Høje-Taastrup at the new center there, where I think it was very well exemplified that even if you do have all the data, you still have a lot of gaps from going from your data to an application layer. And in the smart data world and FiWare and everything, there are dozens, hundreds of models that have to do with buildings. So it's not a big step to get there. The stopping point here is making the collaborations with the people that own the buildings and own the infrastructure. Yeah.
Cool. We're going to see if there's questions online.
There is. Thank you very much, and good to see you, Ben.
Yeah,
so we have a question online, and that's about protection of personal data. How do you secure that no private data is hand over to a third party?
Yeah, great question. So this would be relevant, for example, when we are gathering or we're processing video data. So we have in the lab 6 intersections. All of those are monitored by by cameras, and these cameras are capable of segmenting the images, running various computer vision processes where we get, for example, make and model of vehicles and so on. We do not have any access to the image data. The image data is processed 1 image at a time on the edge, and what's exposed from there is GDPR compliant data. For example, a red Mercedes is driving east at 30 kilometers an hour. So we have kind of written ourselves out of any GDPR issues now, but there is and there will come an issue as these digital twins become more sophisticated that you are capable of recognizing, I saw your car leaving that place, driving this route, and then coming to this building, so I make an assumption that the person that lives at that address works here. And that's personal information. So I think there will be some, GDPR now is our perspective is very much related to video images. But there will come a point where we need to start handling this kind of the conglomeration of numeric data, which becomes so sophisticated that, especially with large language models and so on, that they're capable of making an inference which can bind Paul's address to his workplace, for example. So I'd say for now, we're GDPR safe, but this may be something, it will be something that we need to address in the future.
Cool. Let's see the time. I think we're out of time for questions for right now, but if you stick around, you can have more questions after Sherry has been on. Thank you so much, Ben.